Okay, so here what we're going to do is we're going to look at some examples of calculating probabilities with sampling distributions. So we've seen how the sampling distribution works, and our standard error formula for a means problem is either the sigma, if we know it for the population, divided by the square root of n, or if we have to, we can approximately use the sample standard deviation divided by the square root of n for a less high quality estimate. If we're using sigma, which we will in our example, we can use the normal distribution. But if we're using the sample standard deviation, we would do the same calculation, but we would do the calculation with the t distribution because we have to account for that additional variability in our standard deviation. If we're also going to look at a proportion example, and if we use that, the standard error is a little different. It involves the proportion, and typically we use the proportion from the sample since we don't have a better estimate. Although if you're conducting a confident calculating a probability for a hypothesis test, then you would have a proposed p-value or proportion value that you're comparing it to, and then you would use that proportion in your formula. But we're going to look at each of these, and again, these are not confidence intervals, these are calculating probabilities. But a lot of the mechanisms are the same. We're basically going to conduct a sort of a normal distribution type of problem, calculating probabilities with that, as we did in a previous video. But now, instead of using just the regular standard deviation, we're going to use a standard error formula in place of the standard deviation. So let's set up our first problem, and then we'll go to Excel and we'll actually look at the calculation. So the SAT has a mean of 500, familiar problem, and a standard deviation of 100. This is sigma in this case. This is the population value. A small private school has 30 students and take the SAT, and they had a mean of 510. What is the probability that any sample of 30 students would score between 490 and 510 on the SAT? So this is a one way of asking sort of, is this a typical kind of value that you would expect from a sample size of 30 students? How likely is it to be within 10 points of the population value? All right, so let's go to Excel and do this calculation. Now, what we're going to have for our comparison point, the observation, is the mean of our sample. And so that we said was 510. The mean of the population is 500. Sigma, that is the population standard deviation, is 100, or if we have a sample that we've calculated this from, we would put S here. The sample size we had was 30, and then we're going to use our sigma over the square root of n to calculate our standard error, which we'll need for the probability calculation. And that is sigma divided by square root of n. And again, this is the value we will use in place of where we would put the standard deviation in a previous probability calculation. Now, in order to get the value between, you may recall that what we need is the probability of less than the larger number and less than the smaller number, and then take the difference. So the smaller number in the range that we were asked about was 490. Everything else is the same. And then because we have sigma and a fairly large sample size, we can use the normal distribution, but I will also show you this calculation with the t distribution because it's really not that different. You can do it basically almost the same way. You just change out t dist for norm dist. So we do norm dot dist. The x value is our x bar value. It's the mean of our sample that we're looking at. Standard deviation is not, the mean is the mu. It's what we think the center of the distribution is. Sigma is not the standard deviation of an individual observation. It's the standard deviation of the means of our sample. And then cumulative is true. And then same thing with our 490, norm dot dist, 490, mean, standard error, true. Or again, you can just copy the formula. And then the difference is the in-between value. So that's going to be this one minus this one. So 41% of the time, we would expect as a probability that we would get a sample. We took 30 students and had them take the SAT that would be within 10 points of the population mean, which is 500. So between 490 and 510. So this is a pretty common value. 41% for almost 42% of the time, you would expect this to be within the range. But that does also mean that sometimes you will get outside this range. More than half the time, in fact, you will be a little bit outside this range. Now, the T version of this is basically the same. I'm just going to copy this. And then you could do this exactly the same way. You would basically just say T dot dist. And these endpoints don't have to be symmetric. So I'm just going to do it exactly the way I did for the normal distribution, X. And to do the T distribution probabilities, you would have to convert these to T-scores. So we would have to calculate, let's say T1 would be 500 minus 510 minus 500 divided by our standard error. And T2 would be in this case, it'll be the negative of that, but 490 minus 500 divided by the standard error. Remember, the T distribution doesn't allow you to have a specified mean in the standard deviation, always normalized. So that is one difference. So T dot dist X would be T1, comma, the degrees of freedom, remember, is the sample size minus 1. And then, again, we would do the same thing, T dot dist. We would use our calculated T-score, degrees of freedom, 30 minus 1, and then true. And then the difference would be the higher one minus the lower one. And you get very similar values, but it's a little smaller. You're less likely in the T distribution case to be close to the center. You're more likely to be further from the tail. And so if you're using an estimate of the population standard deviation and not the true standard deviation, or if you have a very small sample size, you get a lot more variability. And so this probability will account for that. Okay, so let's go back to our second question. So in our second question, this is a proportion question. And again, we're going to think of sort of the mean proportion as the center of our population distribution. And if we don't have any information, sometimes people will use 50% as that probability. But in this example, we're going to use the sample that we were given, 87% as our estimate. And then we want to know what sample size would have a proportion higher than 85%. All right, so let's go back to our calculation. So our center for our distribution is going to be the 87%, because that's what we got from our sample. And we want to know the probability of being greater than 85%. The N that we had was a sample of 500. And then our standard error formula was the square root of our p hat, which is just the estimate for the proportion, times 1 minus p hat divided by our sample size. Typically, as you may recall, for proportion problems, the counts are much larger than for means problems. Otherwise, our margins of errors are huge relative to the percentages. Okay, so, but again, now that we have our estimate and we have, this is going to be our mean in this case, and we have our standard error, which is going to stand in for our standard deviation, we use the normal distribution, never the t-distribution, because the normal distribution is our estimate for the binomial distribution, which is actually behind all of this. X is our 85% value, and in Excel, you can write it as a percent or a decimal. The mean is our 87. The standard deviation is our standard error. Cumulative is true, but my original problem actually said we want the probability to be greater than, and norm dist will give me less than that. So I'm going to do 1 minus. And this is because I use percentages, this is being formatted as a percent. We don't really need this many decimal places. Let's make it smaller. So about 90% of the time we would expect, if in fact the true proportion is 85% of gun owners of the American public wants gun sales to always have background checks and no loopholes, then we would expect that we would get a sample. If we were to take a sample, the probability of getting a sample with the percent 85% or higher, that would happen 90% of the time. So only 10% of the time, or 9.2% of the time technically, would we get a sample, if this was the true population value, a sample that was less than that.